So in this lesson we're going to take a look at how we incorporate our understanding of solving equations and inequalities and mixing in the idea of absolute value. Now, as we know from the past, absolute value bars first off look like this. They're just two little bars on the outside of a number, and they're asking us for the amount inside. In other words, in this case, the absolute value of positive 6. Now what the bars are saying is it doesn't care whether it's positive or negative, they just want to know how many. So in this case we have 6 positives, so I just put 6. Same thing goes for negatives. Absolute value of negative 9, well, there are 9 negatives, but all I really care about is that there are 9 of them. Same thing with larger negatives, or I should say smaller negatives. Negative 15. Absolute value of negative 15 is just 15. And even though it's positive, it's the same idea. Absolute value of 28, there are 28. Oops. Ignore that negative sign there. Okay, so how does that fall into our idea of equations? Well, let's take a look at this example here. Here we've got the absolute value of x equals 4. Well, what we want to ask ourselves is, what can I replace x with that when I take the absolute value of it, I get 4? Well, one answer would be just 4, because I can pop 4 in here, take the absolute value of 4 equals 4. But because of those absolute value symbols and what they represent, there's another possible answer here, and you might have already thought of it. It could also be negative 4. Because when I put negative 4 in place of x, the absolute value of negative 4 is 4. So in this, essentially I get two different answers, the positive version of 4 and a negative version, negative 4. And x could be either of those. So x could be 4 or x could be negative 4. Alright, so let's take a look at another example, slightly more complicated. Absolute value of n plus 2 equals 10. Well, again, we want to think to ourselves, what do I need all this to change into so that when I take the absolute value of it, I get 10 as an answer? Well, of course, one possibility is just 10. I could have it so that n plus 2 will eventually turn into a 10 for me. So that this becomes 10, I take the absolute value of it, and I get 10. Or there's the other possibility. Because of what absolute values do with negatives, I can say to myself, n plus 2, I could also need that to change into a negative 10. Because when this becomes negative 10, I take the absolute value of it, I get positive, or I just get 10. So now I basically get two different equations, the positive version, the negative version, and then I solve them. In this case over here, I get n equals 8, or over here we solve n equals negative 12. And if we go back and check, both of these work. 8 plus 2 is 10, absolute value of 10 is 10. And is negative 12. Negative 12 plus 2 is negative 10, but then I take the absolute value of it and I get 10. So I get two different answers for the same problem. Alright, one last one. Now notice on this last one, there's something outside of the absolute value symbols, and so before we can start using this logic of the positive and negative versions, we have to isolate the absolute value part of the problem. In other words, we have to get rid of anything that's not in the absolute value symbols, like this 3. Now, we can't do this like distributive property because technically these aren't parentheses, so I can't do distributive property, but this does represent a times 3. So what I'm going to do is I'm just going to undo it. I'm going to divide by 3. What I do to one side, do to the other. And now I've got what I want. I've got the absolute value part of the problem isolated by itself, and now I can think of it in terms of two different versions. I need this y minus 5 to turn into a 7, or I need that same part of the problem, y minus 5, to turn into a negative 7. Now I solve each of these. Y equals 12. Over here, y equals negative 2. So I get negative 12 or negative 2. Or sorry, positive 12 or negative 2. And if I again go back and check, 12 minus 5 is 7. Absolute value of 7 is 7. Times 3 is 21. Take my other answer, y equals negative 2. Negative 2 minus 5 is negative 7. Absolute value of negative 7 is 7, and 7 times 3 is 21. And so that's how we incorporate absolute value into the solving of equations. Alright, so let's take a look at this next example. Here we've got the equation 2 times the absolute value of n plus 4 equals 16. And just like the other examples we did prior to this, what we want to do here is we want to first isolate the absolute value part of the problem. This 2 on the outside, is just, it's too much at once that we want to think about. So we want to undo that first. So anytime we multiply by 2, the opposite, of course, would be to divide by 2. What I do to one side, do to the other. And now we've got the absolute value part of the problem isolated. Absolute value of n plus 4 equals 8. And now we can think about it logically in terms of absolute value, positives and negatives. Once again, we look at what's inside the absolute value. And what we're thinking about is, what do we want all this to turn into? Well, we want it to turn into an 8, because when we take the absolute value of 8, we get 8. Or we want it to turn into negative 8, because the absolute value of negative 8 is still 8. So I basically make two equations. We get n plus 4. We need it to turn into 8, or we need that n plus 4 to turn into a negative 8. So then we solve each equation separately. On this equation we get n equals 4, or when we do this equation we get n equals negative 12. And we go back and we check it, they both should work. So let's try n equals 4. 4 plus 4 is 8. The absolute value of 8 is still 8, times 2 is 16. So that one checks out. Take negative 12. Negative 12 plus 4 is negative 8. We take the absolute value of negative 8 is 8. 8 times 2 is 16. Both problems work, or both answers work, and we've solved this inequality. Now that we've taken a look at equations with absolute value, what about inequalities? Well, take a look at the example we've got here. And to help us, we're going to use a number line graph to think about this situation. Absolute value of x is less than or equal to 5. So think about what numbers would work. So, positive numbers, if we start with the easier ones first, absolute value of a positive number doesn't really change it, so we can consider numbers like 1, 2, 3, 4, and since it's less than or equal to even 5, we can consider the numbers in between, like 1.5, 2 3/4, 0. So basically, we can consider all of these numbers here as values for x that work, all the way up to 5. So I'm going to put a closed dot at 5. If we go beyond 5, it no longer works. Now normally, this would just be a closed dot and then an arrow to the left, but now think about the negative situation. Can I do negative numbers? Well, with absolute value, yeah, we can, at least to a degree. Let's try negative 1. If I put in negative 1, I take the absolute value of it, I get 1, and 1 is less than or equal to 5. And I can keep going. Negative 2 would work, negative 3 would work, but as you think about it, the furthest I can go is negative 5. Because if I take the absolute value of negative 5, I get 5, and 5 is less than or equal to 5. But if I go beyond that, like let's say negative 6, absolute value of negative 6 is 6, and 6 is not less than or equal to 5. So what I end up getting with this inequality is no arrows at all. I end up getting a starting point of negative 5, an end point of positive 5, and a line in between. So this is almost like two different inequalities saying, okay, on this end of things, x has to stay greater than or equal to negative 5. But then at the same time, I've got a limitation on this side saying that x has to be less than or equal to positive 5. And I say the word and because all these numbers meet both requirements. I have to stay above negative 5 and at the same time stay below positive 5. So I get basically a compound inequality in disguise. This absolute value inequality becomes this compound inequality. Let's take a look at another one. Let's look at absolute value of n is greater than 3. So if I start thinking about numbers, 3 doesn't work, but if I just go just above 3, that'll work. So like 4, 5, 6, 3.5, 3.1. So this would be one of those situations where I draw an open dot at 3. I want to start at 3 but not include it because there's no equal sign, and everything above it. And normally this is where I would stop, but with absolute value, once again, I have to consider how this changes negatives. In this case, I could do numbers like, let's say, -4, because -4, when I take the absolute value of it, is 4, and 4 is greater than 3. -5 would work. Absolute value of -5 is 5, and 5 is greater than 3. Now -3 would not work because once again no equal sign, but let's say I did -3.2. -3.2 absolute value is +3.2 or just 3.2, and 3.2 is greater than 3. So that would work too. So on this side I get a starting point of -3, and this time everything below it. So in this case what I get is two different inequalities. On the one hand, n can be any numbers less than -3, or if they don't fit in this group, then I've got this completely separate group over here. So in this case we use the word or, because I can never be in both groups at the same time, but I'm either in this group or my numbers are in this group, which is n is greater than 3. So again, it's kind of like a compound inequality in disguise, but in this case it's an or statement because I'm either going to be in this group or I'm going to be in this group, but my number can't be in both groups at the same time. Alright, so that's a little bit about inequalities with absolute value. Let's take a look at the next example on the next slide. So let's take a look at our first example with inequalities, in this case greater than or equal to. Now in this case we've got 2 times the absolute value of v plus 5 is greater than or equal to 13. And so just like with equations with absolute value, we want to first accomplish getting the absolute value portion of the problem by itself. So in this case, just like with an equation, we're just going to undo things. In this case the plus 5, we undo it by subtracting 5. We get 2 times the absolute value of v, these cancel out, is greater than or equal to 8. Then we get rid of this times 2 by dividing by 2, and we get the absolute value of v is greater than or equal to 4. Okay, so now what we want to do is we basically want to think about what v could be. And I think the tricky part here is it's all about absolute value. That absolute value, if it's positive, it stays positive, but then if you have a negative number, it becomes positive, or it gets rid of the negative sign. So let's actually think about that in two separate stages. Let's think about all the positive numbers that would work here. Well, you could have v being anything bigger than 4, so 5, 10, 100, or we get really close to 4. We could do 4.1, 4.5. But anything greater than or equal to 4, and in that case the equal part, 4 itself, could work too. So when considering positive numbers, we could say that v can be anything greater than or equal to 4. Okay, just like the inequality here, except no absolute value. Alright, now let's think about negative numbers. What negative numbers would work here? So like if I plugged in -3, would that work? No, because the absolute value of -3 is 3, and 3 is not greater than or equal to 4. But what about -4? Would -4 work? Yes. Absolute value of -4 would be 4, and 4 is greater than or equal to 4. So then what other numbers? Well, -5 would work, -20, -100. So basically, starting at -4 and then going backwards on the number line, it could be any of those negative numbers. So what we get is v could be, in this case, less than or equal to -4. Because we're starting at -4, but for all these other numbers we're actually having to go less than that, backwards on the number line. So again, -10, -20, -100. So we actually get the reverse inequality here. It's flipped around. So what we get is two entirely separate categories. V can be anything bigger than or equal to 4, again, 4, 5, 6, 20, 100. Or V could be any number equal to -4 or less than that, because again, we were picking numbers like -100, but since the negatives go backwards, it's less than or equal to. And since this category of positive numbers and this category of negative numbers are totally separate categories, we want to say or. V can be any of these positive numbers in this category, or V can be any of these negative numbers in this category. And what we essentially get is almost the same thing as what we've got here, except we've got the positive version where V is greater than or equal to 4, which looks almost identical to our inequality here, just no absolute value bars. But then we've got a negative version right here, which has V, and then because this is -4, the inequality got flipped to less than or equal to -4. So basically what this was a compound inequality like we've learned about before, except just kind of in disguise. Once we got rid of that disguise and got rid of the absolute value, we've got our compound inequality here. Now you don't have to think about this logic every single time, so kind of an easier way to think about it, well, I wouldn't say an easier way, but a way to memorize it is look at the original inequality, in this case greater than or equal to. And a little trick for remembering that is this. This symbol can be said as more than or equal to, or greater than or equal to. So something one of my students came up with a couple years back was to think of it as more than or equal to, where it's an or statement. Or another way to think about it is greater than or equal to. Kind of a silly way to remember it, but at the same time, sometimes the silly ways kind of just stick in our head. So this is how we take our inequality with absolute value, solve it to figure out what compound inequality it represents. Alright, let's take a look at this next problem. Absolute value of x plus 4 is less than 7. Now in this case, part of the work's been done for us. The absolute value bar part of the problem has been isolated, so now we need to do like in the last video, basically break it up into its two possible ways of thinking about it. So one way to think about it is just kind of look at it the way it is with just considering less than +7. So basically it's just that inequality without the absolute value bars. X plus 4 is less than 7. But then because of these absolute value bars, there's all these other possibilities where negative numbers, when we take the absolute value of it in here, become positives, and again we get some other answers we wouldn't normally consider. Now to do that, just like again in the last video, you rewrite it, basically creating a negative version of the inequality. X plus 4, we're going to make the 7 into -7, but in the process of making that 7 a negative, we flip the inequality the other direction to greater than. Now, earlier in this lesson we had talked about certain graphs where one set of data and another set of data, they basically overlapped each other. And we called those AND statements because the number for x or n or whatever you're solving for had to not only work for one inequality, it had to work for the other one. Okay, and this would be one of those cases, and it's because of this original symbol of less than. And just like in the last video, there's a silly way to remember it. One of my former students came up with. Think of this as less than. So just in the other video, it was more than or greater than. We knew it was going to be an or statement. When it's less than or equal to, we think of it as less than. Silly, I know, but hey, you'll remember it. Alright, so now we solve these two separate inequalities by subtracting 4. On this side, we get x is numbers less than 3, and over here, x is numbers greater than -11. So we're looking for numbers less than 3 and at the same time greater than -11. And so that would be the solution to this inequality with absolute value.